All right, jumping into chapter 2, there was a bunch of examples from chapter 1 that we didn't go over that you're encouraged to go over because they do cover some somewhat important like problem types, and the answers for those are written in the upper right corner. If you're using the annotated notes, they're all blocked out, so that's what I would recommend doing them on, and then retry them or check your answers with the original notes. So we're going to jump in and talk about atoms and elements, and we'll try to not get off on too many side roads. If you were to take a pencil and you were to cut a piece of graphite on the tip of the pencil, and you cut it, and you just kept cutting it into smaller and smaller pieces, could you divide it forever? Any guesses? No, you would not be able to cut it forever. You would end up eventually with individual carbon atoms. Carbon is what makes up graphite. The word atom that we now use to describe a single unit of an element comes from the Greek atomos, and that atomos word means indivisible, so it can't be cut or divided. So you can't break it down anymore. So once we get down to an individual carbon atom, if we were to divide it, cut it up into smaller pieces, it would no longer be a carbon atom. All of the ordinary matter, everything that we encounter in our daily lives, that is matter, is composed of atoms. It's composed of these little individual building blocks of different elements on our periodic table. And so if we can understand how those atoms behave, that can give us some understanding, some insight into the way that matter behaves as well. If you've taken a biology class, you might recognize the words Brownian motion. Way back in the day, a couple hundred years ago, almost 200 years ago, Robert Brown looked through a microscope. He looked at water suspended particles from pollen grains. And if you clicked the link to the video, which I'm not going to do because in the past that's bricked my stream, but if you click the link, it should be a little video of through a microscope, basically water, and you see all these little particles, and they're like jumping around, and it looks like they're alive. So what's causing that motion? The particles themselves are not actually alive. That's what he thought initially. However, eventually he figured out that that motion must not come from the particles themselves. So something is causing these little tiny particles to jump around seemingly on their own. Einstein, Albert Einstein, big brain guy, developed a theory that explained Brownian motion, and he explained it as the result of molecular bombardment. So molecular meaning we're working with things that are made of atoms. These things are just flying around constantly. They're constantly in random motion. And those bombardments, the way that those things hit other particles, cause little jolts. So sometimes like a couple of, like 2 particles maybe will come together, or 3 particles might come together. Let's say that our pollen grain is this square. So these little molecules maybe of water might all suddenly hit this pollen grain at the same time, and then it gets imparted with a bunch of motion, a bunch of energy in one direction, and that just causes it to get jolted over a little bit. Because they're so small, they can get moved around by just these random fluctuations in water molecules. There's a similar thing that happens with waves out at sea. Occasionally, just the way that the waves line up, you end up with really, really tall waves. This happens sometimes if you're like shaking a drink around. Sometimes randomly the waves stack up and it just like explodes out of your glass. That's sort of the same thing here, but instead of exploding out of the glass, it's imparting energy into the little pollen particle. And so this causes these really, really small particles to oscillate around. And so this Brownian motion infers the existence, or clues us into the existence of atoms, because there has to be little things that are bombarding these pollen molecules. And that was later confirmed by Jean Perrin, who knows. Some other work with atoms much more recently, in the lifetime of people that we know. In the 1980s, Some scientists at IBM in Switzerland developed the scanning tunneling microscope, STM, scanning tunneling microscopy. And basically what this is they took a tiny little needle, they developed a really special tiny little needle that hovers over the surface of whatever it is that you're looking at. And it's got a little bit of an electric force that it can detect, and it can move up and down, or it can detect the current over this distance. And it's basically like a little tiny scanner that goes back and forth that they can use to take pictures of atoms because of how small the little tip here is. STM can also be used to move individual atoms and molecules. So some scientists wrote in Japanese these kanji for atom, so the characters that represent atom. So they took a copper surface, that's the background, there's all the blue stuff, that's copper, and then they used that little needle to kind of nudge these red iron atoms into place to spell that kanji. There's also a link here. This goes to A Boy and His Atom. That's the world's smallest movie. I think the frame size is like, it's a couple nanometers by a couple nanometers. So it's like extremely small, thousands of times smaller than millimeters. So that's kind of fun. It's a little stop motion film that they use the same method for. To give us an idea maybe of how small this is, if you took all of the books in the Library of Congress, which is about 35 million books, probably more now, it's 840 miles of shelves. So imagine the largest library that you've ever seen and then make it way, way bigger. If you were to write all those books using letters the same size as those kanji characters, these little atomic characters, it would all fit in an area of 5 square millimeters. So all of the books in the world would fit in a little tiny patch that could like fit, you could fit multiple of them like on your little pinky finger, on your nail, because of how small the atoms are. Okay, here's our definition for atoms. An atom is the smallest identifiable unit of an element, and elements, there's 118 elements that we know about. And those elements are all found on a table. Does anyone know what that table is called? The periodic table of the elements. And we've got that in the class. You also maybe have that yellow sheet handout. I think I gave that to us on Monday. So our periodic table in the class is a little bit outdated, but every single one of those squares on our periodic table, that's a different element. So they're all distinct, separate, different elements. They have all been named as of like 2019. So the UUT, UUP, UUS, UUO, those all have actual names now. Not that it really matters to us. Okay, so our atoms, that's the smallest little chunk, the smallest piece that you can have of one of those 118 elements on the periodic table. People have had ideas of elements and atoms, especially atoms, for a long time. So back in the 5th century BC and similar times, so think 2,500 years ago, people had ideas about atoms. Some people proposed that matter, if you kept chopping it up infinitely, you would eventually run to a point where you couldn't break it down anymore, and that's where that atomos comes into play. They had some ideas about different kinds of atoms existing. They thought maybe they have different shapes, and they figured that they move randomly through empty space. And later, theory crafters. Siri thought that I was talking about her because I said theory. Later, theory crafters had other ideas about that as well. But 2,500 years ago, they didn't really have very much technology, and so they couldn't test the merits of those ideas. Aristotle's view prevailed because he was a big deal. You've probably heard of him. And because of that, he had ideas about like basically everything being composed of elements, which is not true. That kind of stalled science, stalled thinking about that idea of atomos, or atoms, for a long time. Much more recently, in the time that our country's been alive, chemists like John Dalton have come up with ideas or offered support for the ideas of Leucippus and Democritus, the guys that came up with the idea of the atom. So we've got an atomic theory. The atomic theory states that matter is composed of atoms. Who remembers what makes something matter? What constitutes matter? There's two characteristics for matter. I think we've talked about them. One, has mass. Does anyone remember what two is? Occupies space. So all matter, anything that has mass and occupies space, is ultimately composed of atoms. You can cut it up finer and finer until you end up with those tiny little bits, or you could zoom in, zoom in, zoom in, zoom in, until you get to those tiny little building block pieces, the atoms. And there are a couple of laws that people came up with throughout the ages that support the idea of atoms. So one of them, the law of conservation of mass, proposed by Antoine Lavoisier, states that in a chemical reaction, matter is neither created nor destroyed. Just as a general note, usually the law is more important than knowing like who came up with it or when it was formulated or how they came up with it. So it was formulated by Antoine Lavoisier, but we don't really care that much that it was him or when it was. We mostly care about the results. The law of conservation of mass. So if we do a chemical reaction, matter is not created and it's also not destroyed. It is conserved. Same amount of mass before as we have after. So mass before the reaction should be equal to the mass after the reaction. And this is consistent with our atomic theory, because our atomic theory says that if you zoom in, or if you cut it up into finer and finer pieces, you end up with little indestructible bits. And if those little bits are indestructible, and you do a chemical reaction, basically you're taking those apart, and then you're rearranging them some other way. You could think of this as if you have a Lego set that you love, and if you have siblings, or if you have younger cousins or something, and they find out that you've got this awesome Lego set, and they're like, I want to play with it, and then they smash it into a billion pieces. And then they are like, we're going to make this other cool thing, and it's really not as cool. But they think it's cool, and they just make something else with all the same pieces. They hopefully have not eaten any of the pieces or lost any of the pieces. And so in theory, right, you could pull apart their cool creation, cool in air quotes. You could pull that apart and rebuild your original set because they haven't destroyed any of the pieces. We still have them all. They've just been rearranged. But it is annoying to have to put them together again. I've got 4 younger siblings, so lots of taking stuff apart and putting it back together again. As an example, one reaction that we can do, sodium comes as a solid. It's a metal. Chlorine gas, Cl2, is a gas. If you react these two together, it produces sodium chloride, which is table salt. So in this example, we've got 7.7 grams of sodium. We're reacting that with 11.9 grams of chlorine gas. So that gives us a total mass of our reactants, the things that react, of 19.6 grams. So that's before we do the reaction. And then we do the reaction represented by our red arrow here, and it produces this NaCl. And notice that it's also the same amount. It's 19.6 grams of NaCl, and that is our product. In theory, anytime that we do a reaction, the amount of reactants that we started with in terms of the mass should be the same as the amount in mass of our products. Let's see how well we understand our law of conservation of mass. When a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. What happens to the matter that composed the log? Is it the matter that composed the log reacts to form gases that are released into the air? Is it the matter that composed the log is converted into energy? Or is it that the matter that composed the log is still present in the ashes but has a much lower mass? Take a moment, think about it. Which one do we think it is, A, B, or C? It's A. So the matter that composed the log turns into gases, which we'll find out later is things like CO2 and water, but also the smoke that comes off of a fire, especially like when you first get it lit and it's not running super hot. That smoke is the matter that composed the log, but it's turned into a gas or more of a gassy form. And so it's getting released. And that's why the ash weighs less, is because we've lost some of our initial mass of our log because it turned into a gas or floated off some other way. If you were to burn that log, but you collected it all, so you had like a closed container that you did the burning in, and you collected all that soot and gas and other stuff, it should still weigh the same. And that was like what Antoine Lavoisier did for his experiments. Another law that supports the idea that things are made of atoms is the law of definite proportions, and our definition for that is here, all in bold. So Joseph Proust, another French chemist, formulated this idea. The law of definite proportions states all samples of a given compound, so like one particular chemical, regardless of the source or how they were prepared, so it doesn't matter where it comes from, as long as it's that same chemical, it's going to have the same proportions of the elements that make it up. So basically, like one example, if our given compound is water, because water is a compound. So any sample of water from anywhere in the world, no matter how it came about, should have the same proportions or same ratios of the elements that make it up. So the decomposition, if you can break down water with electricity or something, you take 18 grams of water, it'll result in 16 grams of oxygen and 2 grams of hydrogen. And so we get a mass ratio. This is that proportions part that we were talking about in the definition. It's going to have an oxygen to hydrogen mass ratio of 16/2 or 8. Or we could also call it 8:1. And that 8 would be referring to grams of oxygen, the 1 referring to the grams of hydrogen. Because we specified that it's an oxygen to hydrogen ratio, so the oxygen comes first, the hydrogen comes second. You can also do it with multiple, so we could have 3 or 4 elements, and we could come up with a mass ratio for them. We could also flip it, and then it would be the hydrogen to oxygen, and it would be 1:8 instead of 8:1. Just stuff that we can do. Might show up in a problem on the exam. Do we have questions so far? We're kind of cruising. Cool. So the law of definite proportions, let's look at an example of that. The mass ratio of nitrogen to hydrogen in ammonia is 4.7:1. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? So what's some information that we're given? We're given a ratio, and the ratio is nitrogen to hydrogen, and that ratio has the number 4.7:1. So the 4.7, is that our nitrogen or hydrogen? That's our nitrogen. So 4.7 grams of nitrogen to 1 gram of hydrogen. And this we can basically use as a conversion factor. So if we swap out the colon here, we make it an equal sign. For every 1 gram of hydrogen we have, we would expect to have 4.7 grams of nitrogen. We were also given this 10.0 grams of hydrogen. We've got our question word, how many grams of nitrogen? So we're looking for grams of nitrogen. We can go from grams of hydrogen to grams of nitrogen using this ratio, this chemical conversion factor. We're starting with 10 grams, so 10.0 grams hydrogen. We have grams of hydrogen, so the 1 gram of hydrogen part is going to go on the bottom when we're using this as a conversion factor. And then on the top, we put the other one, the one we're going to, 4.7 grams of nitrogen. Grams of hydrogen on the top, grams of hydrogen on the bottom, those cancel out. So we'd put into our calculator 10 times 4.7, and we would get 47 grams of nitrogen, maybe with different number of significant figures, but the 4.7 that we have was 2. So 2 sig figs makes sense. We would just select D for our answer. All right, one for you to think about, do some calculations with. We've got 2 samples of carbon monoxide. That's a chemical. Those are decomposed into their elements, their constituent elements, the things that make them up. Sample 1 produces 17.2 grams of oxygen, 12.9 grams of carbon. The other sample, sample 2, produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. So how are we going to show that? How would we show that they're the same thing, the same chemical? We'd find the mass ratio, and if they have, what are we looking for with the mass ratio? The same ratio. So find a ratio for sample 1, find a ratio for sample 2, and see if they're the same. So we need to come up with some ratios. We need a ratio for our first sample. So sample 1, we've got 17.2 grams of oxygen, 12.9 grams of carbon. It doesn't matter which one we divide by which one. If we divide with the bigger one on top and the smaller one on bottom, that'll give us a number that's bigger than 1. If you do it the other way, you'll get a number that's smaller than 1. It doesn't matter as long as we're doing the same thing for both of them. I'm going to do oxygen to carbon. So we're going to take 17.2 grams of oxygen. Oxygen gets shortened to O. Divide that by the 12.9 grams of carbon, which gets shortened to C. And we get a number out. 17.2 divided by 12.9. We get 1.33 repeating oxygen to carbon for sample 1. For sample 2, we have 10.5 grams of oxygen, 7.88 grams of carbon. We're going to do the same calculation. It has to be the same calculation. So 10.5 grams of oxygen divided by 7.88 grams of carbon. Calculator says 1.33. There's some other stuff after that. We're going to round it for 3 significant figures. So we're going to stop at 1.33. The next numbers are 2, so that would round down. And that's going to be also oxygen to carbon. So we got the same ratio of oxygen to carbon. So it's consistent with the law of definite proportions. Since sample 1 and sample 2 are both water, just from different sources, we got the same ratio. That's a good sign. Questions? We also have the law of multiple proportions. For our law of multiple proportions, box this in red. This one was published by John Dalton. We'll see his name show up again. The law of multiple proportions says that when 2 elements form 2 different compounds, so you've got 2 elements, you make one compound out of them, but you can also make a different compound out of them. The masses of one element that combine with 1 gram of the other element can be expressed as a ratio of small whole numbers. So if we take chemical A and combine that with chemical B, we've got 1, 2, 3 or more atoms of chemical B. That would have, for 1 to 1, 1A to 1B, it's AB. If we've got 2 Bs, it's AB2, or AB3 if we've got 3 Bs. So the masses of B related to A are also related as small whole number ratios. So AB1, basically 1B per A, AB2, 2 Bs per A. We wouldn't be able to zoom in, especially not in 1804. We wouldn't be able to zoom in and see that it's that number of Bs for every A, whatever the chemicals are, or that number, 2 Bs per A. What we would have been able to do back in this time is get the mass of AB1 and the mass of AB2. So that's how we would work our way to figuring out that it's 1B or 2Bs. So we're going to look at carbon monoxide and carbon dioxide as our example compounds. So carbon dioxide, the di means that we have 2, and our oxygens are here on the outside. So we've got 1 carbon, 2 oxygens, versus carbon monoxide, we've got 1 carbon, 1 oxygen. The mass of oxygen that combines with 1 gram of carbon, so if we've got 1 gram of the carbon part, we're going to have 2.67 grams of oxygen. For our carbon monoxide, there's only 1 oxygen, and so that mass is going to be 1.33 grams. Some difference because of rounding. If we take the ratio of those masses, so the mass of oxygen to 1 gram of carbon, so doing that same ratio that we did before, mass oxygen to 1 gram carbon in CO2, it's that 2.67 number. If we do the mass of oxygen to 1 gram of carbon in carbon monoxide, it's the 1.33 number. So we're dividing those two, and we get a value of 2. This 2 means that carbon dioxide has twice or 2 times the amount of oxygen compared to carbon monoxide. Which in our modern day and age is not really that profound of a conclusion, but is a little bit of relevant chemistry history. All right, an example using this concept. Hydrogen, one of our elements, oxygen, another element, form both water and hydrogen peroxide, and those are different chemicals. The decomposition of a sample of water forms 0.125 grams hydrogen for every 1 gram of oxygen. So water gives 0.125 grams hydrogen to 1 gram of oxygen. That's important information. Let's pull that out. 0.125 grams hydrogen H to 1 gram of oxygen O. The decomposition of a sample of hydrogen peroxide forms 0.0625 grams of hydrogen to every 1 gram of oxygen. So hydrogen peroxide our ratio is 0.0625 grams hydrogen also to 1 gram of oxygen. And we want to show that these results are consistent with the law of multiple proportions. So for the law of multiple proportions, we're going to take the mass of an element to 1 gram of another element, on top in our first chemical, do the same mass ratio on the bottom, or divide them, and we should get a whole number. So if we take this 0.125 grams, 0.125 grams over 0.0625 grams, we get a value of 2. So the relative number of hydrogens in water, there's relatively to the oxygen, there's twice as many hydrogens in water versus in hydrogen peroxide. That's the takeaway there. And this law of multiple proportions is important because it shows that we've got, we're increasing the number of the constituent elements, in this case the hydrogen. We're increasing that in like whole number ratios, meaning that we're only increasing by like, we have twice as many hydrogens. We've got 4 times, 3 times, however many times more hydrogens. We're not getting like 2.5 times the number of hydrogens, or like 1.34 times the number of hydrogens. It's always a whole number, so that's more evidence that these are made up of atoms, that we've got small individual units that we can't cut into further pieces. So that's sort of like the important part. We're not going to probably mention law of multiple proportions again after chapter 2. It's like most of these laws, except for law of conservation of mass, they just show up here. Okay, John Dalton, we talked about him a little bit before. Last time was 1804. In 1808, he explained these laws, those 3 that we just talked about, with his atomic theory, Dalton's atomic theory. Dalton's atomic theory has a couple of ideas to it. We've mentioned some of them before. So each of our elements, anything that's on our periodic table of the elements, is composed of tiny indestructible particles. We call those atoms. So they're made of atoms. All of the atoms of a given element, so for any of the elements on the periodic table, if you were to look at all of the atoms, line up like 500,000 of the atoms, they should have the same mass and other properties. So atoms of an element are the same, are all the same. So every atom of oxygen is going to be exactly the same as every other element or atom of oxygen. We can combine the atoms in simple whole number ratios to form compounds. Why can we only do whole number ratios? Why can't we do like half an oxygen atom? You can't have half of an atom. So following from point 1, they're tiny indestructible particles, so you can't cut them in half. That's why we're always going to have whole number ratios. Like if we were making student groups, I wouldn't be able to assign a student group that has half of a student in it because somebody would be going to jail if that were the case. So whole number ratios because the compounds are made of atoms and the atoms are tiny and indestructible, so we can't cut them in half. Atoms of one element cannot change into atoms of another element. So if you've got, for example, this is what people were trying to do with alchemy, that thing that they reference in The Office, right? Hg there, mercury, is right next to gold, Au. For the longest time, people were like, maybe we can turn, especially lead, maybe we can turn other elements into gold, and then they'll be much more expensive. We can like magically turn all of this sort of useless lead into gold and then sell it, and then we'll like, profit. You can't do that, or at least not in Dalton's atomic theory. You can't do that. So we can't turn lead into gold. We can't do that with any of our other things. And in chemical reactions, atoms only change the way that they are bound together or linked or grouped or paired with other atoms. So they only rearrange, essentially. And in our modern era, especially with that STM, that little like needle microscope thing that we were looking at, we've got really good evidence for the existence of atoms. We've basically got pictures of them. You can't actually take a picture of them, but we've got the next best thing to a picture. Questions about our atomic theory? I'm going to let you in on a little secret. A little secret about the atomic theory. It's not entirely true. So some of these things are wrong. Isn't that fun? All right, some more history. J.J. Thomson. Thomson's another big name in atomic history. Thomson constructed a partially evacuated glass tube, meaning that he took out a lot of the air inside of a glass tube. He called it a cathode ray tube. So this cathode ray tube, he put a high voltage, so he connected some electricity. Here's his tube. Took a bunch of the stuff out. He's got a negative side, he's got a positive side, and he put a really high voltage across the tube. And that high voltage ended up resulting in a beam of something that traveled from the negative side to the positive side. So he noticed a beam of something going on in there, and he called that beam of particle cathode rays. What are the initials for cathode ray tube? CRT, which is not critical race theory. It's a different CRT. Does anyone know where CRT shows up? There's another place that it shows up. We're maybe mostly too young to know CRT. It's a type of TV. So CRT also shows up in those old, the really big boxy TVs, the ones that make like a little hum and there's the static on the front. That's the CRT part. It's this thing. Okay, so because of those cathode rays, Thomson investigated those particles, and he figured out that A, they travel in straight lines, which is cool. They are independent of the composition of the material from which they originate. So you can use anything as your cathode, any material as a cathode, and you're still going to produce cathode rays. Basically saying everything, anything, can make cathode rays. That's all we're saying there. And they also carry a negative electrical charge. So like how magnets have a plus side and a minus side, sort of a similar thing here. So these are negatively charged little particles. And as a reminder, in case we haven't played with magnets in a while, they're so fun, why wouldn't you play with magnets more? If we've got a positive and a negative, those are going to attract, opposites attract. That's true for these. Positive charges will repel other positive charges. Negative charges will repel other negative charges. And for positive and negative charges on this scale, they can cancel out. This is also actually true with magnets. You can also get magnets to cancel out if you get the positives and negatives lined up just right, which is kind of neat. So we've got negatively charged cathode ray particles. They travel in straight lines. Everything can make them. Some more investigation with some crazy maths. They took a different type of evacuated tube, it's this horn-looking thing, and they set up the little cathode ray station here. So he's making cathode rays, and he put a little hole in the anode, which is a tiny little hole. So we're shooting the cathode rays at this anode, the positively charged part, but because there's a hole and they travel in straight lines, they just go straight through it. So our cathode rays fly through it, and then we've got some charged plates. And because they're negatively charged, they're going to fly away from the negative side, and they're going to fly towards the positive side, so they'll get deflected by a little bit. And using some physics, knowing the strength of the magnetic field, how fast they were traveling, making some assumptions, measured a value of this many coulombs per gram, and coulombs is a unit of charge. So we got this value for the charge on these cathode rays, which, spoiler alert, they're electrons. You don't need to memorize that number. This data implied that the cathode ray particle, what we now know as the electron, was about 2,000 times lighter than hydrogen, which is crazy because hydrogen was the lightest known element. And because it was lighter than that, then that means that it was smaller than the lightest known element. And so the big takeaway here is that the formerly known indestructible atom could actually be chipped. You could take parts off of an atom. So Thomson had discovered the electron. The electron is negatively charged. It has a 1- charge, and it's got a really low mass. It's also present in all atoms. So that's why all material, any material that he used for the cathode, would produce these because they all had electrons, so they could all eject or lose electrons. A lot of this is just history stuff. Another experiment, Robert Millikan performed this famous oil drop experiment that's kind of crazy. I'd recommend watching one of the videos about it if you're interested in it. But basically the idea is they took some oil, they atomized it, so they made it into a fine mist, and sprayed it into a chamber. There's a positively charged plate up here on the top, there's a negatively charged plate here on the bottom, and we're also injecting this source of ionizing radiation. So there's ways that you can make basically a particle beam. So the particle beam hits these little nebulized or atomized drops of oil, and it imparts them with some charge. So now we've got little charged oil drops, and because the oil drops are charged negatively, they're going to be suspended. The positively charged plate is going to be pulling them up. The negatively charged plate at the bottom is also going to be pushing them away. And then there's a light source in there and a microscope. And so they looked through and they would estimate the size of the oil drop, and figuring out based on like the positive charge and the negative charge, they could figure out how much charge is on the oil drop. They could also estimate based on the size of the oil drop that they saw what the mass of the oil drop was. And so through this experiment, he was able to figure out the charge on a single electron. Because we already knew the mass to charge ratio, this number, we already had the coulombs per gram. So Millikan was able to use this coulombs per gram number to figure out the the charge on a single electron. It's all stuff that we kind of just skim over. But basically he found that the charge on any drop was always a whole number multiple of this number. And so he figured out that this number must be the charge on a single electron, since they're all multiples. So that they might have had 2 electrons worth of charge, or 3 electrons worth of charge, or 5, or 15, or 25. But they all boil down to having this amount of charge. So with that charge number and knowing the coulombs per gram that we saw earlier, they were also able to figure out the mass of an electron, which is 9.1 times 10 to the minus 28 grams, which is like an absurdly small number. I'm going to write it out because I feel like doing that. So in standard notation, that would look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14. That many grams. So that's like that's just a crazy small number. And they were able to figure that out in the 1800s, 1900s, before we had the scanning tunneling microscope or any of those cool, fun gadgets that we have now. So that's kind of neat. Discovering the presence of electrons led to some other questions. If there's electrons in atoms, how does that work? like where are they, how do they exist, like what's the system, what's the makeup of an atom. So if there's negatively charged electrons in there, if it was just negatively charged electrons, they would just all scatter because they would be repelled from each other. They would be repelling other electrons. So that means that there has to be some positive charge in the atom. So how do we mix these positive and negative charges into our atom? Are they solid spheres? Do they have some sort of structure? And so what J.J. Thomson came up with is this plum pudding model, Thomson's plum pudding model. So in Thomson's plum pudding model, you've got essentially, you could think of it, instead of plum pudding, like think of it as like yogurt. So we've got a big blob of like yogurt or cheese or something, and that's all positively charged. And then inside of that, we've got raisins or chia seeds or other things that are just kind of floating in and dispersed in that, and those are our electrons. So electrons as particles dispersed or spread out in a blob of positive charge. So we have little like chunks of I'm trying to think of the little balls of chocolate. That might be a better example. We've got little blobs of chocolate, and they've got stuff in them. They're not just chocolate. They've got other goodies in them. Truffles. Okay. And now we're going to take a very brief aside to talk about radioactivity. So radioactivity, which I don't think we cover that very much in this class. You would have covered it probably a little in Chem 20, hopefully, a little in Chem 20. Radioactivity is the emission of small particles from nuclei. We haven't learned what nuclei are, but that's the center of atoms, basically. So the emission of particles essentially from atoms. Specifically, one part, the nuclei, and we're just mentioning it briefly because there's another experiment that requires us to have some basic idea of what radioactivity is. So there's three types that we're going to mention. We've got alpha particles, we've got beta particles, and we've got gamma rays. Alpha particles are positively charged, not infinity. Alpha particles are positive, and they are also the biggest form of radiation, the most massive form of radiation, which is relevant for our next experiment, which is Rutherford's gold foil experiment. So in 1909, Ernest Rutherford, who worked with Thomson, performed an experiment. He wanted to confirm Thomson's plum pudding model. So again, in the plum pudding model, we basically just got globs, think yogurt or like soft mozzarella cheese. And inside of those globs, we've got little particles kind of dispersed throughout them. So in his experiment, Rutherford took positively charged alpha particles. Again, these are big particles. And he shot these particles at really, really thin gold foil. So a little thing of gold foil, and then he had an alpha source that was shooting particles at it. We'll see a picture of that on the next one. In the plum pudding model, mass and charge are spread all the way throughout the volume of the atom, and there aren't any hard bits inside of it. And so the prediction was the particles are going to go straight through the gold foil, especially because it's really thin. They're not going to get stopped up because of the consistency issue or anything like that. They're just going to zoom right through. So this is basically the setup for Rutherford's gold experiment. So he took a source, some lead to stop the radioactivity from going everywhere. He directed this beam at the really, really thin gold foil, and we expected that all of the particles would just go straight through and not get deflected. However, some of them get deflected off like to the side, which would indicate that they hit something because these particles travel in straight lines. Some of them even bounced back, essentially. So they hit something and then bounced basically a 180 ricochet and hit the detector way back here. So that is not good news for our plum pudding model. I'd also like to take a little aside, because this is actually like a crazy experiment. So this detector part, the way this detector works is it lights up when it gets hit with a particle. How would you know if it had lit up? You'd probably have to see it, or you'd have to have some like tool that can tell if it's got lit up. Do we think that in the 1900s, the early 1900s, we had like light detectors that could hook up to a computer because we didn't have computers, and then we would be able to just tell where all the light was showing up? We did not. And so somebody would have had to be there looking at a little section of this detector, and that's what happened. So undergrad students whose names are mentioned usually in the history books, basically just sitting in the dark, staring at into the dark. Basically, like if you go to the optometrist, hopefully you go occasionally, especially if you need glasses like me. They'll sometimes do a little test where they have you look at this little dot, and then they're like, let us know when you see the blurry bits. It's sort of like that, but just sitting in the dark, and then like every time you see a little light, make a little check mark. So students sitting in the dark for hours on end, just staring at a blank screen in the dark, waiting for light to show up. That's how they detected that. So that's kind of crazy. So the results were not what we expected with their plum pudding model. Most of them passed directly through, but some were deflected back. 1 in 20,000 apparently bounced back. Rutherford was quoted as saying, about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. A 15-inch shell being like a bullet that a ship would fire, 15 inches in diameter. If you shot that at a piece of tissue paper, or just any piece of paper, and it bounced off and came back and hit you, that's how credible the plum pudding model was, essentially. So they were very, very surprised, and they concluded that the matter, the plum pudding model, must not be as uniform as it seemed to be. So what they thought that probably was instead is that there was a lot of empty space. So that empty space would let those particles go through. And if you've got a thin enough sheet, then there's going to be enough empty space that a lot of those particles can pass through. And so that's what we're seeing with these straight lines. Those will pass through. They're not going to interact with any of the electrons. However, we must have a hard center in there somewhere that those alpha particles can bounce off of. And that hard center is our nucleus. I think we've got nucleus here, yes. So Rutherford proposed nuclear theory, the theory of the nucleus. I'm just rewriting it as theory of the nucleus. You don't have to do that. And it had 3 basic parts. So those 3 basic parts, these are some good ideas to know. Most of the atom's mass and all of its positive charge are contained in a small little core, a small little center called the nucleus. This is the center of the atom, usually how we conceptualize it. So we've got a little tiny super dense core, and that's got most of the mass, like 99% of the mass, and all of the positive charges, all in this nucleus. Most of the volume of the atom is actually empty space. And in that empty space, we've got our negatively charged electrons just kind of dispersed like as a cloud. And then the third point, and this is very important for our conceptualization of atoms, there are the same number of negatively charged electrons as there are positively charged particles. So the number of electrons equals the number of protons. Those are the positively charged particles. So outside in our little cloud, we've got all of our electrons. We have the same number of electrons in our little cloud as we have protons in our little center, our little nucleus. So if we've got 5 protons, we have also 5 electrons. Draw a little, we'll do a helium nucleus. So the protons will be the red there, and then maybe in purple, we'll have these little electrons, and the arrows are just showing that they're flying around. Two protons, so we've got 2 electrons as well. And that makes it neutral. The positive charge balances out the negative charge, so there's not an overall charge for the atom. Questions about any of our very fun history so far? Cool. There's another part. Rutherford's model was really successful. However, they realized that it was not entirely complete. So for example, hydrogen contains 1 proton. Helium contains 2 protons, but they know through their calculations, their math, their experiments, the mass of helium is 4 times the mass of hydrogen. So 2 protons instead of 1 proton, but it's 4 times the mass, which doesn't make sense. It should be 2 times the mass because it's got twice as many protons. And James Chadwick and Rutherford figured out that that previously unaccounted mass was due to neutrons. Neutrons are neutral. And they are also in the nucleus. We also say this on the next slide. So neutrons have no electrical charge. They are neutral. Another thing about neutrons is that they're similar in mass to protons. Normal hydrogen atoms just have 1 proton and no neutrons, but helium is 4 times as massive because it has 2 protons and 2 neutrons. So we've got protons and neutrons in the nucleus. And where are our electrons? Where do those live?
The electrons on the outside?
Around the nucleus, yeah. So protons and neutrons, that's our dense little core, and then we've got electrons flying around the outside. Our nucleus is super dense. It's over 99.9% of the mass of the atom, but it's really small. And then the electrons are sort of like water drops in a cloud. They're there, but you're not really sure necessarily where they are. They're really small. They're spread out. And so atoms are still mostly empty space. If a nucleus was the size of a period, like this one here maybe, the electrons would be 33 feet away, 10 meters away. And that, the period on the board in the projector, probably bigger than the size of the period for that nucleus. So these are really, really spread out, lots and lots and lots of empty space. Another analogy is that if you have something like this scaffolding structure, if you look at it kind of from a distance, it might start to look solid. If you get in closer, you'll realize that there's lots of empty space. This is also sort of like if you go out into like a meadow or anywhere that there's grass. Initially, it looks like, okay, we've got solid grass here. If you get close enough, and you start peeking around in between the blades of grass, you'll notice, well, there's things that live here. There's actually a lot of empty space between the grass. And that's a similar thing to the way that atoms are. Despite having these mostly being made up of empty space, right, we still run into matter. Even though it's empty space, we can't just like walk through walls or anything like that. Okay, more about our subatomic particles. All of our atoms are composed of these three particles, are protons, neutrons, and electrons. Which one of those three is positively charged? Protons. Which one is negatively charged? Electrons. Which one is neutral? Neutrons. Correct. And our proton and our neutron are about the same mass. They're expressed here in kilograms because that's the convention. So if we look at the mass of our proton and the mass of our neutron, they're both times 10 to the minus 27 kilograms, super small. And they only differ after the third decimal place. So the proton in the third decimal place has a 2. The neutron has a 4. So it's very, very slightly more massive than a neutron. The mass of the electron, on the other hand, is 10 to the minus 31 instead of 10 to the minus 27. You don't have to have these numbers memorized either. But you should know, right, the mass of the electron, this is a lot smaller than 10 to the minus 27. The mass difference is about 2,000. And so the example that we have here in this slide that shows up in our book is that if the electron is a grain of rice, then our proton is a baseball. So think of a little tiny grain of rice. If your friend throws one grain of rice at you and hits you in the face, probably not that big of a deal, even if they're a really good thrower. If they're a really good thrower and they throw a baseball at you and hit you in the face, maybe we're going to urgent care or the emergency room, right? We'll probably have a pretty big bruise. Not fun because of the difference in mass. There's another two things that are about 2,000 times in difference that are much bigger, and I like this analogy. So if our electron, instead of being a grain of rice, is a watermelon, any guesses on what's 2,000 times more massive than a watermelon? Not a bowling ball, much bigger.
Swimming pool?
Probably not a swimming pool. Not a planet, not quite that big. So if the electron is a watermelon, then our proton or our neutron is a semi-truck. So that's also about a 2,000 times difference in mass, just on a bigger scale. Usually when we're talking about really small particles, rather than expressing them in this scientific notation with units of kilograms, instead we talk about them in terms of atomic mass unit. And our atomic mass unit is defined here. It's based on the mass of a carbon atom. So it's 1/12 of the mass of a carbon atom that has 6 protons and 6 neutrons. So in our minds, we can sort of think of it as approximately 1 AMU for the mass of a proton or a neutron. So proton and neutron are approximately 1 atomic mass unit. That makes things a lot easier to work with because now we're working like 1, 2, 3, 4, 5 instead of like something that's a crazy small number like 10 to the minus 27. Also important, I mentioned this before, but we've got it written down here in italics for some reason. The charge of the proton is equal and opposite to the charge of the electron. So the proton is opposite charge and size to the electron, despite them being very different in terms of their mass, right? So a proton is about 1 AMU, and it's got a +1 relative charge. An electron has an AMU of 0.00055, and it still has the same size charge, just opposite of our proton. So even though they're different sizes, one's a +1, the other's a -1, and we'll usually think of them in terms of 1 plus minus 1, or multiples of plus and minus single numbers, rather than talking about their charge in C or Coulomb, because also that's not a very fun number to work with. We'd rather talk about plus and minus, plus 1 minus 1. Another thing that I'd like to point out, some of you, if you're very astute, might notice that our mass for our proton and our neutron are both above 1 AMU. But it's based on 1/12 the mass of a carbon atom that's 6 protons and 6 neutrons. So 1/12, when we've got 12 particles, it should be on average 1 AMU, but they're both above 1 AMU. And if you're curious about why that is, you can read into mass defect. So the mass defect changes particle mass when they bond together and form atoms. That's not going to show up on an exam. I just think that it's interesting, and it's something that there's probably a really good YouTube video on somewhere out there. Okay, and we'll get towards wrapping stuff up in a moment. We're getting close. What am I doing? Okay, got my controls back. Matter, things that have mass and occupy space, like tables, chairs, people, are normally charge neutral. They're not positively charged, they're not negatively charged, because our protons and our electrons are present in equal numbers in any of our atoms on the periodic table, normally. But we can get charge imbalances, and those charge imbalances usually equalize quickly. So think about electricity strikes. That's a very large scale electrical charge imbalance. We get a big buildup of negative charge, and that all releases at once in a giant shock of electricity. This also happens when you get static electricity. So like in the dryer, you pull your clothes out, and you've got a sock in there and it's stuck to something else. That's static electricity. That's also a charge imbalance. Static electricity, like when you touch a metal object or another person, and you get that little zap, that shock, that's also charge balancing itself out. Okay, I wanted to get a little bit into elements. So we've got elements here on our periodic table. What's the smallest piece of an element? What do we call that? One piece of an element.
Atom.
An atom. So our elements are defined by the number of protons. Elements are defined by the number of, and I'll write out protons here, the number of protons. So if an atom has 1 proton, that makes it hydrogen, anything that has 1 proton. If it's got 2, if it's got 3, if it's got anywhere up to 118, we've got an entry for it on our periodic table, and it's defined based on the number of protons. The number of protons is also called the atomic number, the number of whatever type of atom it is. It's got the symbol Z. It's from the German Zahl, which means number, so Z is our symbol because it's number. So Z means our atomic number, the number of protons. And on the periodic table entries, normally that number is up at the top. In the one that we have in class, it's in the top right. So if we look at the big key, the BR, the 35 in the top right, that is the atomic number. So that's the number of protons that bromine has. BR is for bromine. Other elements like helium have 2. Carbon is going to have 6 protons in its nucleus. We are not specifying anything about the number of neutrons here. Usually there are neutrons in there as well. So again, on the periodic table, our atomic number is usually listed at the top, and again, that's our number of protons. That's what makes something an element. So the element symbol, the name, the atomic number, those are all linked together. If you change one of them, you're also changing the other two. We'll talk about symbol very briefly because it's the 2 of 2. Each element is identified by that unique atomic number, always a whole number. So you're never going to have like 114.3. It's always going to be either 113 or 114 in that case. They're also going to have a unique chemical symbol. So anytime that you see a chemical symbol, this is like sort of like zip codes, more like state abbreviations, like CA is for California. It's always for California. If you write CA, that always means California. It doesn't ever mean any other state. It's the same way for our periodic table symbols. Our chemical symbols are always either 1 or 2-letter abbreviations. If it's 2 letters, even if it's 1, it's always that the first letter is capitalized. Always. Always capital when we're talking about the symbol. We're always going to capitalize the first letter, and the second letter is always lowercase. So CN with capital is not the same as capital C lowercase n. Capital CN would be carbon nitrogen. Capital C lowercase n was, I believe, copernicium. Some of our chemical symbols are based on English names, which is great for us since I'm assuming that if we're here we speak English. Some of them are also based on Latin names, which if you speak a language other than English is also probably good news for you because you might know some of those names. And so the symbols might come more easily to you. So things like Na for sodium comes from the Latin natrium. Other countries, a lot of the elements have different names called different things. I would recommend practicing learning the name and symbol combinations for most of the upper block of the periodic table, focusing especially on the upper rows. It's like the first 4 rows. At least I would recommend having all of the name and element symbol combinations in your brain. And I think I have a quiz for us on that on Canvas if you want to practice it. It's not for points, it's just for practice. Questions at all? Cool.